Next up, now that we kind of have an idea of what vector-valued functions are, we're going to talk about limits of vector functions. And while I think that the first part of this was, a pretty natural progression of where we've been, I do think a lot of people get intimidated about limits and maybe don't enjoy those so much. So don't worry, we're going to go through this deliberately, and it's not going to introduce anything really wild compared to limits as you learn them in prior classes. First, I'm going to talk about some basic properties of limits, then we'll do some examples. So, limits of vector functions work like you would expect. What I mean by that is that properties of sums and multiples of limits that you remember from prior classes are still going to hold. So if you take the limit as t goes to any value of a sum of two vector functions, that's just the same as the sum of the limits of those two functions. If you have a difference, of course, it's the same thing, minus there and minus there. If you want to take the limit of a multiple out front of some f, so maybe you have some lambda, where lambda could even be like a function of t. So it's weird. I checked before I started writing that that thing wasn't there, and now it's returned. Really can't figure it out. Okay, so if you have a constant out front of a limit, usually you can just pull that separate from your limit, and that's going to be true here. You can just look at your lambda of t by itself, its limit, multiplied by the limit of your capital F. And then kind of the thing that maybe you wouldn't have as much intuition for is the limit of dot and cross products, because dot and cross products are unique to vectors, but they're going to just sort of pass through the same way multiplication does. So you're going to have limit as t goes to t0 of f dotted with the limit as t goes to t0 of g. And that's going to be the same. I'm not going to rewrite it. I'm just going to do that, erase it. You can do some kind of slashing or whatever you want. I'll just write in parentheses also for dot. But yeah, so both of our vector, quote, multiplication operations, dot and cross products, pass through the limit the way you would think. And then the definition of a limit is related to continuity in the same way as for scalar functions like you learned about in probably Calc 1. That relationship being that basically continuity means a limit exists. So f of t is continuous at t0 if the limit as t goes to t0 of f of t is equal to f of t0. So, all these things that I've written down about vector functions can look intimidating when they're on paper. There's all these equations and they all have limits in them, and most people don't like limits. But these are just things that you should already feel like you understand about limits. I'm not telling you anything new. These are all the rules about limits that you should have held on to from prior classes. So, kind of the lesson here is if there's something you think you can do with a limit to a vector valued function, you probably can. The only thing that you really need to know separately is that to compute limits of vector value functions, I think I've been doing, so VVF, take your limits component-wise. That's just going to mean separately for each component. You take the limit of the I hat component, the limit of the J hat component, and the limit of the K hat component when you actually want to compute that. And we'll go ahead and do some examples of those separately. That way you can go back to them later on.